This is a work done with a master's student, Sofiane Ait-Hamadouche, and a colleague here at the INS Paris-Saclay, also associate professor, Amelie Fau. So the background of this study is the importance of the precise projection of elasticity if you want to assess the risk of cracking cement-based materials. So if you use even simple approaches to determine the cracking risk, where we need a good estimation of the elastic properties. If you use more sophisticated nonlinear analysis, you also need, as a main ingredient, the elastic behavior of the material. If you look at the problem at early ages, it becomes more interesting because the elastic properties changes with the age. It becomes a real challenge to estimate precisely how these properties will evolve with age. So that's the context, is how it's related to the topic of the conference. So what we want to do is to establish this kind of correlation here between the composition, the structure, the microstructure of the material, and the properties that the material may have or should have. We can look at both ways, this kind of correlation, in a way in which we try to understand the behavior of the material, looking in the composition, in the microstructure of the material, to understand why the material has given behavior, why it's cracking under certain conditions. Another way of looking at the same problem of establishing this kind of correlations is to try to define a given performance, a target performance, a target property. Let's say if you want a material that comply with a certain criteria regarding cracking or elastic properties, and how we can optimize the formulation, mixed design, in order to comply with the target performance. So we can look at the problem both ways. So now the question is how to establish this kind of correlation. We have four main strategies. So the historical, fundamental one is the empirical science. So we do different formulations. If you consider cement-based materials, we do different formulations, changing, for example, a given variable in our mixed design, for example, the water to cement ratio, the type of cement, etc., and try to look at what is the property, the performance that you have. So that can be tedious, that can consume energy and other resources, but that's what most of the research community has focused on for the last, let's say, decades, even the last century. The other three paradigms are related to model-based approaches. For the model-based approaches, you have micromechanics that arises as a very good candidate to establish composition microstructure property correlations. More recently, not that recently, we can also use computers to do simulations and try by means of numerical samples to estimate and understand, and why not also optimize the behavior of in applications for cement-based materials. And the fourth paradigm, the most in vogue that you see studies more recently, is related to data-driven science, in which if you have a reliable database, we can try to make some projections and analyze the data in the database in order to gather knowledge and new information that can be useful. And you can also use this kind of strategy to establish composition microstructure property correlations. So what I propose here in this presentation is to look at the second and fourth paradigms and try to combine both approaches as allies to establish composition microstructure property correlations for elastic properties. So here, just a quotation to reinforce the motivation of this work. If you can understand by means of models what are the physical origins of behavior, and if you have a reliable databases with which we can compare our model estimations, so that can be really a huge thing for the optimization and for the prediction of the properties of cement systems, and that can also be useful for designing for service life. So that can be a really interesting path in which the research community should invest in the following years. So the goals of this presentation, of this work, is to combine, as I said, a data-driven approach with machine learning and micromechanics-based approach, a model-based approach with analytical formulation in order to establish the correlation that I just have detailed. Here we focus on elastic properties on very simple systems, also ordinary Portland cement pastes, because it's a simple system. If we know how to use this strategy for these simple systems, then you can build confidence and try to extend to other more complex and relevant cement systems. So the idea is first to predict the elastic properties from the composition. From the composition, we predict the elastic properties, and then try to see if you can do the reverse path. And for a given target elastic property, try to predict the composition of the system. That can be useful, for example, if you want to optimize the system, but also for forensics purposes. That's why the name of the study. So we can try to do investigation and try to determine the composition from the elastic properties. Is that possible? That's a contribution that can try to answer, at least start to answer this question. So materials and methods, the first important thing to do is to collect the data for the database construction. So we looked at the literature. So here we can see there are more than 5 or 8 references, several studies, the experimental studies in which people has measured the elastic constants of cement pastes, OPC cement pastes. The measures of the elastic properties are dynamical. So for all the database is consistent in that way. There's no quasi-static measurement. So the statistical parameters of the data collected are listed here in the table. So as input, we look at the composition of of the OPC in terms of clinker minerals. Also the age quantified via the degree of hydration, and of course the water to cement ratio. As main output, the elastic constants. For this presentation, I will focus on the young models because it's the most used and important for cracking analysis, but we also consider the other elastic constants that you can see in the following. Then the methods for machine learning, we adopted 2 methods. So artificial neural network and Gaussian processes. We are not looking at how the parameters that we can use for both approaches can affect the estimations. The goal here is not to develop a new algorithm for machine learning, but to apply what already exists. So we are using these 2 methods here already built in Mathematica software. We try other algorithms that you can also find in Mathematica, and we compare the performance with respect to the experimental data in the database. And you can see here more dispersion in the points means that the performance of the predictions are poorer. So as you can see here, Gaussian processes, neural network in nearest neighbors are the best performance for the estimations according to the database. If you look at these two quantifiers of error, so here I use the root mean square error and the mean error as estimators of the accuracy of the methods for the four elastic constants that you can see. So Young modulus, Poisson ratio, bulk, and share moduli. So as first results of what I'm showing here are some predictions regarding observations. They are not included in the training data set. So the results that I showed here was for the training data set with the 365 observations. Then we predict experimental values for other authors that are not in the training data set to see if we can get this kind of prediction for new data. And what is interesting here is that some of the experimental observations for these authors here are not dynamical measurements of the elastic properties. So even for quasi-static measurements, we can see that we can find good estimations in some cases. Looking a little bit more in details for the case of Tamtia, it's a quasi-static measurements of the Young modulus. We can see all the machine learning methods gives a reasonable good estimation of the Young modulus. I'm comparing here with some micromechanics based estimations that also performed quite well in some cases. And we can see that we have a nice framework to estimate properties using both methods, machine learning or micromechanic basis approaches. So now, okay, you can use both strategies to predict properties concurrently. Can we also combine the two approaches to have something in which you can improve the accuracy of the predictions in a data-driven strategy? So the idea was to use one of the micromechanics approach here, the one with the best performance. It was Murray Tanaka considering three scales. So the representation of the microstructure that I have adopted is here as the top of the slide. And you can see the performance in the comparison of experimental values and estimated values in the B picture. The black circles are for results concerning late ages, and we can see for late ages this micromechanics-based strategy yields good estimation for the results. It's not that interesting for early age results, but I mean it remains with interesting accuracy. The idea here was to first look at the database and identify where are the domains in which there's data missing. So the approach adopted was to look at the distance in between the different observations per input dimension. So we look at each one of the, we have here 7 inputs, and we see where are the zones in which two points are far from the farthest from each other. So with this approach, the values that are listed here at the left are the points in the middle of the zone in which we have missing data. And what we have done after that was to use this micromechanics approach here to generate new data, and then put this new data in the database in which machine learning would be trained after. And we see when you do that, so the minimal new data that you can do with these values here are 6 observations, but you can also, generate more data doing combinations of the different values here. So we tested with the minimum data, new extended data set with the 6 observations collected from a combination of the data here, and also a new extended data set with 24 new observations. We added these new observations to the original training data set. And what we see is that with the extended data sets, we can decrease the average standard deviation. That means we can improve the accuracy of the machine learning prediction. So we can use, we can generate new data with a micromechanics-based approach, and that new data can be used to improve the accuracy of predictions in data-driven approach using machine learning. Yes, so if we go back to the goal, another thing that we wanted to do, it was to predict for a target elastic response, the composition of the material. To do so, what we have done was to adopt a Monte Carlo machine learning approach. So we generated several predictions, 10,000. We did 10,000 Monte Carlo trials per dimension of the input vector. So our input vector has 7 dimensions. So we did 7 times 10,000 MC trials. And then in this new generated data, we look for the values of the projections that comply with the target elastic response that we are looking for. So we can get some distribution per input component, per component of the input vector, and see with what are the distribution of the input regarding the target elastic response that you are looking for. So here, what I'm showing is the distribution of the values, and when we adopt this target here, so the 16 more or less 2 gigapascal that I took for experimental study using quasi-static measurements of the young modulus. And the distributions are here. So you can see that for Gaussian processes, the distribution includes the experimental value, so that's a good thing. But the distributions are quite large, so the broadness of the distribution cannot help us in determining the composition, but that can be useful somehow in seeing that we can have a variety, a huge variability in the composition of cements that yields the same elastic response. Okay, so to conclude, what I have proposed here is to combine machine learning and micromechanics-based approaches as allies to establish composition microstructure property correlations in cement-based materials, starting from the elastic properties. So both methods have some nice and bad points associated with that I listed here, but that can be a promising strategy for establishing this kind of correlations. So the next step is to consider other properties, and why not? We can include the strengths for which micromechanic-based approaches are more difficult to be adopted, and also other properties that can be of interest in cement and concrete research. Thank you.